Hello and welcome to our MAE 535 presentation. I'm Nadeem Ansari.
My name is Glen, Lawson.
I'm Keegan, Brochu.
And my name is Abdullah, Zafar, and we're going to do wireless power transfer.
Like a boss!
So the way we're going to achieve wireless power transfer is by using this guy here. As you can see, it's a simple coil made of magnetic wire. We're going to pass a time-varying magnetic field through the center and using Faraday's law of induction produce a voltage that's going to power a secondary load. And the way we're going to produce this time-varying magnetic field is by using Ampere's law and sending a time-varying current through the primary side, and once it goes through the coil it'll produce a time-varying magnetic field through here. But the problem doesn't stop there. The big piece of this project is going to be actually coupling the two, and the way we're going to do that is by calculating the resonant frequency of the secondary coil and oscillating the primary coil to that frequency and getting the best match, and then doing a little something extra towards the end.
Alright, I'm going to go ahead and explain to you the circuit that we built to do wireless power transfer. So we start off with a simple DC power supply that runs to our primary circuit board. And on our board we have a MOSFET that could be controlled by a function generator, but those are pretty expensive. So we decided to use a Arduino microcontroller to control that gate. And we just need to use a simple processing program language from a computer, and we wrote in a specific frequency for that gate, and through that gate runs a DC power supply to the primary loop as well as a small capacitor parallel to it. So I'll go ahead and turn on a power supply like a boss, and using low voltage and low amps, we can go ahead and power. Let me go ahead and raise our primary loop, and there you go, wireless power transfer. Okay, no, but seriously, here's our secondary loop.
So our secondary loop has an identical coil to the primary loop, and in parallel, circuited in parallel to it is a capacitor and two LED diodes. An LED diode is unidirectional current, so if you run current one way, it'll light up, but if you reverse it, it will not light up. So these are actually circuited opposite to each other. So when we bring it close to the primary circuit, you see that one of the diodes lights up. And then if we reverse it, reversing the current, the other diode lights up. And the reason for this is the MOSFET is getting triggered open and close by the Arduino chip, basically fluctuating the current from 0 to about 0.3 amps and up and down, but it never reverses the current in the primary loop. So the direction of the magnetic field formed by the primary circuit never changes, only the magnitude changes.
We can also vary the geometry of our primary coil. Here we have a coil that's 15 centimeters in diameter versus the original one that's 5 centimeters. As we bring that close to our secondary coil, we can also see that the light illuminates, the LED illuminates. Also, as we reverse it, we can see similar effects to the previous coil. In order to get the larger coil to work, we do have to decrease the frequency by a magnitude. We also have a small cone here that we can implement in our primary loop. It has 40 turns as well, just like the large coil. And as we bring that close to the secondary loop, it also illuminates the LED. Of course, there are inefficiencies present with our coupling that can be improved. As we can see, our range is only in the 1 to 2 inch range distance between the primary and secondary coil. If we use a better matching network to fine-tune our frequency, we can better optimize our capacitor's involvement in the primary and secondary loops.
So as you can see, it's not hard to achieve wireless power transfer, it's just hard to achieve wireless power transfer that's efficient. We hope you enjoyed our video, and we gotta get some homework done.